You can go ahead and start.
Okay. Yeah, I was trying to see how many people we have on. Welcome everybody to our first seminar of the new year. Today I am welcoming. Oh, I gotta find the material I need to read. Today we are welcoming Patrick Murphy. Patrick is a grad student at the University of Washington, working under his advisor, Cliff Mass, on understanding the relationship between weather and wildfires. Currently, he is finishing up 2 papers on the meteorology of California wildfires, which is the subject of his master's thesis. He will defend on March 9th at UW. After receiving his master's, he plans to continue into the University of Washington PhD program with Cliff. At UW, Pat is also associated with Abby Swan's Eco-Climate Group and has taken forest and fire ecology courses with Ernesto Alvarado and Brian Harvey of the Forestry Department. Prior to attending grad school at the University of Washington, Patrick received his bachelor's in atmospheric and oceanic science from the University of Colorado Boulder. While there, he did research in wind energy, participated in multiple field campaigns, and worked year-round at the National Renewable Energy Lab, NREL. As an undergrad, he published first author work on the relationship between operational wind turbine power production and wind shear. He helped co-author seminal research on wind turbine wake steering and won an AMS Undergrad Research Award for work with crops and wind energy. Beyond all that, he enjoys rock climbing, and he promises climbing is not why he attended CU Boulder, and he's into photography. So let's welcome Patrick and see what he has to say today. Thanks for joining us, Patrick.
Thank you very much, Chris, for the kind introduction. I'm going to share my screen now, so let me know if it's all working. Cool. As Chris mentioned, my name is Patrick Murphy, and today I'm going to be talking to you guys about the research I've been doing with my advisor, Dr. Cliff Mass, on understanding the meteorology of California wildfires. So we're going to be talking about some relationships, thresholds, trends in these fires at pretty high spatial and temporal resolution. Before I go too much into the nitty-gritty stuff, I do want to do a quick icebreaker because I had to share this with someone, and I think I've seen a couple Cal Fire people join the talk. While I was in Eidlingen, Germany recently, visiting my girlfriend's family, a little village outside of Stuttgart, I found a Cal Fire truck. So if you're missing a Cal Fire truck and want to know where one has ended up, I have found it in Germany. And as I go into my motivation and background, I'm sure I'm preaching to the crowd here, but I do just want to give a quick disclaimer. I mention that fires are a totally natural thing that have occurred on Earth for the last 400 million years, as long as they've had fuels and oxygen to do so. They exist at the intersection of different disciplines, and so I'll be talking about weather today, but there's other stuff going on with them. Fires have helped shape our forests, and then those forests help shape the fires that follow. So we're going to go into some motivation and talk about California. Hopefully everyone here is interested in California, but if you're not already, this might make you more so. I can say that the West has been increasing in burned acreage and damage for the last about 50 years or so. We can see this in one of the data sets that we used in this research, where emissions in 2 fuels types, savanna and forest, have generally been increasing over the last 18 years. We can break this down a bit more and get like the seasonal cycle of fires as well. So they typically happen from like June through October or so, maybe a bit longer in savanna. And then in forest, they typically occur like late summer, early fall. I should mention that emissions here don't equal burned area necessarily. So some recent research has shown that generally burned area is a bit higher in the lighter fuels like savanna, grassland, chaparral, etc. But forest has a lot more carbon in it, so when it does burn, it emits more. And then if I still haven't convinced you that California is very interesting, Well, 54% of the smoke over the central and eastern US is actually due to fires in the western US. So there's lots of health benefits associated in understanding California fires on a far-reaching level. Beyond that, there's been a lot of recent severe fires that have been the cause of a lot of damage, a lot of money, unfortunately, a lot of lives lost, and gained national and international attention. So in 2017, the wine country fires occurred. In 2017, we also had the Thomas Fire in December. That was a relatively unseasonal fire. In 2018, the Camp Fire happened in November. It was the largest global insured loss of that year, and I believe the wine country fires were the previous largest insured loss due to fire. In 2020, we had the largest amount of area burned on record, at least. So the largest fire was the August Complex group of fires. And then these fires in red have led to around 146 deaths, depending on which fires you include, which is really unfortunate. However, just having fires in California is not necessarily unprecedented. The largest fire here was still around 3 times smaller than the largest historical fire that occurred in Montana. And the largest fire, the August Complex, was comparable in size to the 1889 Santiago Canyon fire. And so usually we're familiar with seeing fire trends from like the 50s onward, let's say. We see an increase. But it turns out that there used to be a lot more area burned in general from some research out of the University of Washington a while ago. And so if there were a lot of fires before, why are we concerned about fires now? Well, we're also changing our climate. So for one thing, there's more people at the wildland-urban interface. There's more ignitions leading to a longer fire season. So on this figure, basically anywhere where there's red, there's more human ignitions than natural ignitions. And generally, those occur where people are. So wherever people are, there's more fires due to people than due to lightning. Like I just mentioned a little bit, we've had fire exclusion over the past 150 years or so due to forest management, or I guess mismanagement in some senses. This figure shows that fire relates pretty well to dryness. However, as we've been drying out our atmosphere in recent years, we've actually seen a very large decrease in fire. Though I should mention here that this decrease in fire doesn't necessarily affect regions of severe infrequent fire. So like coastal California, where it's very moist, or the Western Cascades of Washington, for example, might not be affected as much by a fire deficit. And then, like I mentioned a little bit a second ago, we're changing our climate. As we increase temperatures, we increase the amount of water the atmosphere can hold, which dries out the atmosphere. And so some recent research has showed that this corresponds really well to fire area burned. And so projections have been made from some colleagues of mine at the University of Washington and from John Abatsoglu, showing forest fire area trending off into the future as we keep drying our atmosphere. This is all occurring at the same time as the fire deficit. There's more ignitions on top of all this as well. So a lot going on. Now getting to wind and dryness, which is kind of the focus of my talk, it turns out that all of the aforementioned fires that I've talked about specifically were all wind-driven and very dry. And this is a very common theme throughout extreme fire history. My title slide figure actually shows smoke from the August Complex fires and some of the other fires in early mid-September 2020, getting wrapped up into a huge mid-latitude cyclone. And these fires were all, the smoke was all blown offshore by strong offshore directed winds. And it's just really impressive to see the scale of these events occurring. Additionally, wind and dryness can kind of transcend fire severity regimes. So I mentioned Schonagel's work on understanding how fire deficits affect different fire severity regime regions. In that work, they discuss case studies of high severity, low severity, and mixed severity fires. What I found interesting from my perspective of being interested in winds is that all of these fires, all their case studies across the severity regimes were actually affected strongly by strong dry winds. So there's a lot of importance to them. We've pretty much known about the physical effects of wind on fire spread for a long time. So Rothermel developed a semi-empirical model based on wind tunnel and wildfire data that described wind's effect on fire spread. And it's been updated slightly over the past few years because we found maybe that the original wildfire data wasn't exactly what we thought it was, but in general, it still is used today in lots um, of models. Beyond these physical effects, though, I don't think we really have great knowledge of like the observational effects. We focused a lot on individual cases, but we don't necessarily know how fires are affected by wind across the whole spectrum of fire burnings. So we have case studies on a lot of these fires I mentioned before, and some other ones. I've all seen papers written about these. But I think Cliff and I were interested in maybe trying to take a more holistic view of this because of some recent data sets we found. Um, Fire or wind and dryness is also used in a lot of fire weather danger ratings. So indices that have been developed to talk about fire potential given an ignition. So for example, we have the Fosberg Fire Weather Index. This is just a shot of it being run by the University of Washington for some date in 2003. There's other ones like Red Flag or the Fire Danger Rating System, etc. Recently, though, there's been one that's gained a lot of traction. It's a pretty simple index, but I think it's pretty great. And it's called Hot, Dry, Windy. Brian Potter was a part of that paper. I don't know if he's on this call. I can't see it. But I know Cliff and I have talked to him in the past about it, and he's been very helpful with us. Hot, Dry, Windy is something that Cliff runs on our high resolution models in the Pacific Northwest now. And what it does is it takes wind speed and multiplies it by dryness, so vapor pressure deficit. It's really great. However, you're kind of left wondering sometimes if wind speed is what's driving the fire danger or if the dryness is driving the fire danger. And so that's something else we wanted to look at with our work. Additionally, simple wind and moisture can represent more complex indices pretty well. This is from Australia, I believe. And so all you need to know from this figure is that as long as the blue and red lines are lining up, the simple wind and moisture is representing these complex indices that involve knowledge of precipitation pretty well. And it's actually doing it in both grasslands and forest regions, which is pretty cool. So we're going to talk a little bit about the fuels associated with California wildfires and the grasses and forest type regions in California, because those are important to understand for the rest of the talk. So the main types of fuels that I'll talk about today are savanna, which is savanna, grassland, shrubland. It even kind of includes woodland, so like sparse trees interspersed with grasses, and temperate forest as the other fuel. And this is the spatial distribution of them in the data set that we're using. So generally we have savanna in some of the low-lying regions or along the slopes of the coastal mountains. And then we have forest in the north and then along the crest of the Sierra Nevada. However, forests and grasslands aren't just full of live fuels, they're also full of dead fuels. So debris exists like needles, sticks, and logs in both of these land covers, although we don't have access to them with our data set. And so the way that dead fuels work is that, and this shows an example of a slice through some dead fuels on the right. The moisture content of the fuels, because they're dead, mainly varies with the atmosphere, be it precipitation or humidity or sunshine or wind. And the smaller fuels dry out faster and don't really rely on precipitation. So 1 to 10 hour fuels don't necessarily need precipitation for. As you go past that, precipitation starts to matter a bit in forecasting your fuels. And then once you get out to 1,000 hours, it doesn't matter as much for fire spread. Additionally, live fuels can also end up behaving like dead fuels. So grasslands will cure throughout the course of a year, which means that they green up and grow in the spring through the summer, and then in the fall through the winter, they stop growing and eventually die. And by the time they're dead each year, they're considered cured, and they act like a dead fuel So they dry out really quickly with atmospheric humidity. Additionally, large diameter live fuels like big trees can approach the moisture of extinction of a flame by the end of a fire season. So fires can exist on live fuels as well. Now let's talk about California's climate and weather, just as a simple overview, so you can understand what the kind of drying or raininess characteristics of California are. Why is California predisposed to severe fire? Why do we always see fires there? Well, climatologically, there's a Mediterranean climate, which means hot, dry summers and cool, moist winters. So grasses will grow during these moist times and then dry out and desiccate during the next dry season. Atmospheric rivers occur, which are pretty small spatially. So maybe only one part of California actually gets the rainfall that it needs, leading to long-term droughts elsewhere. And then there's typically a stable marine layer of air in the summer, which means that you can't have rising motion and then afternoon thunderstorms to induce precipitation. Meteorologically, or on a shorter time scale, what often happens for these dry, windy events is that high pressure moves into the interior of the US. So that's shown in red on the figure to the right. This high pressure forces cold, dry air from high to low. So pretty much from the red to over the crest of the Sierra Nevada into California. This cold, dry air warms up as it descends from the ridgetop to the surface, and that increases its temperature, drying it even more. And then because you have mountains, you can have mountain waves that accelerate the winds even further. So really fast, really strong, really dry winds. And this figure comes from previous work done at the University of Washington by Brandon McClung, who got his master's with Cliff just a couple years ago. And this figure shows the dryness associated with events similar to these that occur in Oregon. Typically, the events start in like Washington and then progress southward. So Washington, then Oregon, then California could all be hit by the same like dry, windy storm. So we have some research questions from this. How do wind and dryness work compared to each other? Do thresholds maybe exist in wind and dryness where it's dry enough or windy enough? How do these affect different fuels or different subregions of those fuels? What spatial patterns govern the windy and dry events? Do these differ by different regions of California? And then finally, we're predicting the atmosphere to become less windy. We're also predicting it to become drier as we increase temperatures and then decrease the temperature gradient from the equator to the poles. So how does that all affect the fire relevant weather in California? So this might be a bit repetitious, but just some goals and the overview of the talk. I'm going to go through my data sets. So we'll discuss fire emissions, what those look like in California. Then we'll discuss weather during some case studies. We'll even compare daily versus 30-day prior dryness, see how those work for different fuels. And then we'll put emissions and weather together for around 80,000 days of emissions. Show you results from those. Then we'll composite across emissions and show that we believe that dryness and wind do act somewhat differently across the spectrum of emissions, and that there's different spatial meteorology driving those different events. Finally, we'll show some thresholds in dryness specifically, showing that thresholds do exist that guard severe fire emissions, and we'll show trends in those as well. And so the first section is kind of like the first paper we're working on and hoping to publish, or I guess, sorry, submit for publication the next week or two. And the second paper will come sometime after that. So I won't spend too much time on the data sets other than to say that we have basically gridded observations for the last 18 years of emissions and weather over California. The emissions come from satellite burned area that's run through an emissions model. The weather comes from weather models that have been run in using past historical observations. The grids don't actually line up. They're actually offset by half a grid cell because my life would have been way too easy had they just lined up perfectly. And then we have emissions daily and meteorology hourly. And we know fuels as well from the emissions data set. And again, using these, we get weather for around 80,000 days of fire. So let's take a look at the fire emissions first. We're going to look at frequency and severity sort of with this and find that frequency and severity are inverse as we expect. So typically the most frequent fires are agricultural burns through this agricultural Central Valley of California. They happen unseasonally, so in the springtime when it's cooler and moister. However, all of these severe fires occur in regions separate from that, with the Central Valley of California having very little total emissions. So the severe fires all occur late in the year. They're all concentrated along the slopes of the Sierra Nevada, and the northern forests and the northern coastal range. And so frequency and severity does look inverse. These high emissions are often forced by individual events. So here we can see, I don't actually know if you can see my mouse, but this tan area on the northern Sierra Nevada slopes is in November, and that was the 2018 Camp Fire driving that. These orangey dots are associated with the 2017 wine country fires. Additionally, we can plot histograms of the emissions, finding that they cover around 9 orders of magnitude, which is pretty impressive that it can all be picked up. And we also see that choosing emissions greater than a certain amount acts like a spatial filter, as we expect from what we just did. So high emissions fires, which are fires greater than 10 emissions units, are a little bit more common in forests, but very high emissions fires have similar frequency in both regions. So we're going to select fires with emissions greater than 10 and see that it does spatially divide up the data. So we lose all the Central Valley emissions, we lose all of the desert emissions, and we start getting emissions that we care about a bit more. For the rest of the talk, this will be considered high emissions, but we could go higher and start getting individual events maybe that we've studied or really care about. So additionally, beyond emissions greater than 10, selecting a certain region, they only account for about 4% of the total fires, but they actually contribute around 85% of the total emissions due to the logarithmic nature of emissions. And so for all these reasons, that's why we consider it the high emissions threshold. Next, we can consider each grid cell or each contiguous emissions in a grid cell to be one fire for the purposes of this work. I'm going to look at like the temporal evolution of fires. So we find that most fires are actually pretty short-lived. Should have put the numbers on the bottom here, but in savanna, they usually only last 5 days or so. The end point's around 40 days. So emissions peak very early on and then decay rapidly. In forest, they're typically a lot longer lived. Emissions decay much less rapidly. And you can actually have fires that peak over 40 days after starting. So the red salmon fire in Northwest California, we actually found out about this fire because it did peak after day 30 and was associated with those very strong winds that I showed in my introduction, the smoke getting wrapped up into that mid-latitude cyclone. I believe this fire started July 27th and lasted a very long time. So the emissions data set is pretty cool. How about the weather data set? How well does this work at resolving the winds of California? So I'm going to talk about the Camp Fire just a little bit and show that this data set does work well for capturing the dynamics of the Camp Fire. This is what the data set looked like around the time of the Camp Fire ignition. The winds are shown on the left figures, the drynesses are shown on the right figures. The bottom figures show a slice of constant latitude, so what the winds look like with respect to vertical coordinate or elevation. We have elevated winds. We have this spatial pattern of internal gravity waves with high winds and low winds going up perpendicularly from the slope of the terrain. These winds are dragging down air, warming it up, which is why we have increased drying downwind of the mountain slopes. And then we typically have increased dryness past the crest of the Sierra Nevada. So These winds are pretty reasonable as well compared to reality. So the hourly ERA 5 winds are pretty proportionate to the peak gusts that we found at Jarboe Gap. So we're going to use hourly maximum winds later on in this talk. So now that I've described all the emissions and all the weather, how do we actually get wind and dryness, because I have two offset grids. So let's take an emissions grid. We have some weather around it. How do we get winds? Well, we take the 24-hour spatial maximum of the 500-meter layer max wind. So the wind value associated with this would be the high value. The dryness is the spatial mean of the VPD, or the dryness. And it looks a little bit lower, so something like that, just to illustrate how we do it. We additionally calculate our dryness for 30 days prior to every fire emission. We also note the first and maximum day of emissions of each fire. So that way we can look at each fire in an individual sense and not have, one very strong fire just continually like polluting the data set. So here's what results will look like just for one section of these fires, which is all days of the Savannah fires. Wind is on the y-axis, dryness is on the x-axis, and emissions are the colors. So high emissions are the red colors, low emissions are the cooler, like blue colors. Typically, as you can see here, we see a pretty strong relationship with dryness, where as dryness increases, the emissions also increase. I'm now going to complicate this a bit and show you the maximum days, the first days, and forest all in one figure. There are a lot of subplots. So in every case, across both fuels and across all different days of the fire, we see that dryness relationship. We also see a very strong vertical line lower bound in a threshold for dryness relating to these high emissions fires. This threshold is around 15 hectopascals of dryness for Savannah, using the day of dryness, and around 10 hectopascals of dryness for forest. We can next look at the 30-day prior dryness just to complicate this even further and have a ridiculous amount of subplots. And what we find here is that in forest, this actually gives us an improved lower bound threshold. So in forest, this 30-day prior dryness does matter a little bit more than in Savannah. In Savannah, it doesn't really change the dryness that you would get for each fire. Additionally, with this, we find that weather might be a necessary condition, but it's definitely not a sufficient condition. So although we do have severe fires typically occurring at higher drynesses and higher winds, we also have a lot of weak emissions fires where there is a fire emitting and we have very high winds and very high dryness, but the fire emission stays weak. So, we do have to know that in the real world, we need knowledge of emissions and fuels, et cetera, at a higher resolution. So what about wind speed? I think if you squint your eyes, you can maybe convince yourself, as Cliff and I have done, that as you go up on this, the winds increase and the emissions increase, but it's not super rigorous. So what we do next is we composite the emissions with these bins centered around 10 and show results for that. And so I want to talk about all the subplots in detail. We now have wind on the y-axis, emissions segments on the x-axis, and dryness as the colors. You can see, especially on the first days of the fires, the two figures on the bottom, we see a very strong relationship with wind in that severe fire regime. So for fires with emissions greater than 10, all of a sudden, emissions scale really well with wind speed. However, in the other ones, I think we do see a relationship for high emissions fires. It's just not as strong as the first day. And then I should also mention that if we did make the same figure using daily average winds instead of daily maximum winds, we would get the same results, but they'd all just be lowered down a little bit because the average winds are lower we get the same physical relationship between winds and emissions for the high emissions fires. We can also here look at daily versus antecedent dryness. So on this figure, again, the emissions are on the x-axis, and now the y-axis is the difference between the two drynesses. So positive values mean it's actually drier on the day of the fire, and negative values mean it's drier on the 30 days prior to the fire. And we find that for high emissions fires, we actually, in Savannah, have statistical significance where all of the high emissions fires are better related to the day of dryness than the 30-day prior dryness. In forest, we maybe see that with the highest emissions fires, but there's a bit more uncertainty throughout the whole emissions greater than 10 regime. Now, I like this figure a lot. I'll be honest. I think this one's great because it shows how unusual the weather needs to be. I think we can get a lot of information from it. So on this figure, as I mentioned before, that severe weather may be necessary. I think we actually do see that. So all of the highest emissions fires, which are the reddish colors and the darker reds being the highest emissions, all of them for every different day of every fire into the different fuels occur at the highest relative drynesses and winds throughout the data set. So you do need covariantly high wind and dryness for your strong fires. And I'm borrowing my terminology from John Abotsoglu's recent work on Oregon fires because they found similar results, as I will show now. So their x-axis is basically reversed from ours, where it's relative humidity, so lower values mean higher, versus ours using vapor pressure deficit or percentiles, where a higher value means higher. But either way, these black dots associated with the fire are occurring at the highest covariant dryness and wind speed, which is what we saw. So although winds and dryness were each extreme but had precedence, the compound in their data set was unmatched. And they also found that most large fires in Western Oregon in the last 120 years have coincided with similar events. So beyond that, we see another interesting trend on this figure, which is that we can sort of divide up our emissions into two regimes, a moderate emissions regime from green to yellow, and a severe or high emissions regime from yellow to red. Within these regimes, we see that on the moderate regime, dryness increases the emissions, and wind either stays neutral in savanna or actually decreases in forest. And then in the severe regime, we see that wind increases very strongly with emissions, or emissions increase strongly with wind, but dryness does not increase too much at that point. So this leads to a couple hypotheses, which are that the moderate cases might be due to just general heating, kind of boring stuff, where you have maybe like a high pressure and then increase your dryness and have increasingly weak winds. And the severe cases might be due to the passage of like a upper level trough in the atmosphere or winter storms. So I think there might be different dynamics leading to these. So to look at that, to divide up these regimes, we need to divide California into different subregions. These different regions of California might be differentially affected by weather or even just differences in the phase of an upper level trough moving through. So here I show the divisions we came up with. These are somewhat qualitative. We tried to divide California up into relatively equal sized latitude zones to split it up by latitude. And then also, if we couldn't split it up by latitude as much, like in forest, we tried to split it up by general like ecoregions. So that's what this figure shows. We're only going to talk about two subregions today in the interest of time. So the Bay Area for savanna, and then the North Forest region for forest. The variables that we look at for the spatial meteorology are temperature and winds at the surface. And we use anomalies for these because the moderate cases, we're going to use different divisions now in the emissions and just show moderate here. But the moderate cases actually occur all throughout the entire year. And we don't want to just average out weather that happens in the summer with weather that happens in the winter. Interestingly, the severe cases do self-select to be more and more within the fire season. So I will now show results for temperature anomalies in the North Forest, composited throughout all the different days of fire. We'll focus on the moderate section first, which are the top figures. I've just overlaid some dots that show the North Forest is there. And typically we just have elevated surface temperatures during these moderate cases. Temperatures might increase a little bit throughout the moderate cases. That's pretty much it. Just general warming over California and that region. As we go into the high cases, at first it looks like that, but the really high cases start developing this temperature gradient. And by the highest emissions cases, the temperature gradient is super strong with a lot of cooling in Nevada and Eastern California. This temperature gradient is what's driving these strong winds that we can now look at and see that for the moderate cases, winds are pretty weak, but they do increase throughout the moderate regime. And that increasing continues in the bottom row for the high regime, where we have neutral and then stronger winds, and then the strongest anomaly of winds. So that's what it looks like for forest. In the north, the Sierra Nevada region is pretty similar to this. For the Bay Area of California, we get very similar results that look a little bit different. So the moderate cases, again, due to just general warming over California. As we go to the high cases on the bottom, we start developing this strong temperature gradient, and then we do only have one case at the highest emissions level, but the temperature gradient during that case was very, very strong. Again, this drives winds. So in the moderate cases, we have pretty quiescent winds that maybe increase to neutral. And then throughout the high regime, we have stronger and stronger winds increasing monotonically in strength. However, they actually only increase throughout the western part of the Bay Area. And this could be what contributes in part. I know there's contributions of development and fuels, but this could be part of why in the Western Bay Area we see the very strong emissions and not so much out east where we aren't on the slopes of the terrain, etc. And I have a few more minutes, so I'm going to talk a little bit about some of our results from the second paper that we're kind of coming up with, which is on thresholds and trends. As I mentioned before, we have thresholds in dryness that are very rigorous from this work. So vapor pressure deficits greater than 15 hectopascals for day of weather in savanna, and then 30-day prior weather in forest. For winds, we haven't found like a super rigorous one in our data set. 10 works pretty well for this talk. We will just use 13 though, because that's what some prior research from Cliff and his master's student did that they published on in AMS. Although this 13 meter per second threshold might be a little bit too high for severe weather in this data set in California with the resolution that we have. So I'll first start by showing just the threshold attainment by season. If we look at just the vapor pressure deficit threshold, which is in orange on these two figures, we find that we usually reach it in the summer, which is not too surprising. That's when it's hottest and typically driest. We reach it very infrequently in the fall and winter. Wind has the opposite temporal pattern, where we reach it most often as we have storms coming through in the winter, and then we reach it very infrequently in the summer. So together, when we need both of these to happen, we typically see those happen in the fall and the spring. So savanna actually gets a lot more cases in the spring. It's just not really dry enough, and the fuels don't really exist well enough in a lot of cases to sustain fires. However, in the fall, we also see a strong peak in fires, and in forest, the fall is really the season where we have the weather happening. We can also get this trend through time on this figure. So we have our weather data set actually for 40 years now. And so the first 10 years of the data set, relatively weak signal in the fall. that's increased in strength a lot until recent years, especially in savanna, but also in forest. And you could also maybe convince yourself that the peak is moving a little bit later into the year as well. So that's potentially occurring. We can also look at the spatial pattern of these thresholds. So the colors are the days per year meeting the criteria. These are the criteria shown above the figure. So the vapor pressure deficit for savanna and forest, as well as the winds. The statistical significance is shown as a black outline around the dot. So if there is a black outline, it means that there was statistical significance. And basically, all across California, we're reaching these thresholds more often than we used to. It's especially true in the desert in the southeast, but it's also true along the slopes of the Sierra Nevada, just north of the Bay Area, some of the southern coastal regions as well. Most of these trends are actually contained in the late fire season alone. So just September, October, and November, we've seen about an increase in a week per year meeting the thresholds than we did 4 years ago. These thresholds are not being driven, or the total thresholds are not being driven by wind. It is actually getting less windy across much of California. These are mostly insignificant trends. They're pretty weak. I can also say that the daily mean shows different results than using the daily max. But in general, it is getting a little bit less windy across much of California, though it's not true for every region. Dryness, however, is a completely different picture. The entire region has gotten statistically significantly, basically more dry, where many, many more days per year are meeting this dryness threshold. So overall, those trends that we showed are being driven by dryness rather than wind speed. So that wraps up my talk. I'll just give some conclusions. We looked at distributions of fire in meteorology, found that dryness might be more important for moderate fires, wind might be more important for severe fires, but both are necessary for severe fires. These patterns, or these moderate and severe fires, are driven by different spatial patterns that do have some differences depending on what ecoregion of California you're interested in. We've also found that we think lower bound thresholds exist, especially in dryness, although emissions do scale continuously with dryness, but it can work as like a good enough value. And then severe fire relevant weather has increased in frequency across much of California. So we're not just looking at trends in emissions, but just the weather. And so if the weather is continually getting worse, maybe that is affecting the emissions somewhat. This is driven by dryness with wind becoming less frequent. So in the future, we do want to submit this for publication sometime soon, hopefully. As Chris mentioned, I'm submitting my master's on Sunday or Monday. So a week or so after that, maybe I need like a day of rest between those periods. Then we also might want to look at higher resolution fuels, maybe a bit more with antecedent conditions. We also want to look at trends in the future. So do some dynamic downscaling of climate to weather models and see if these trends continue on, and then maybe add some more synoptic weather into this. And so with that, I guess I can pass it back over to Chris and the Missoula people, and you guys can help lead the discussion. So thank you guys so much for having me.
Thanks, Patrick. That was great. Really interesting material. And I already have several questions in the chat box. I'll start with those. Anybody with questions, or since Kristen Allison sent in an early question in chat, so I'll start with her, but you can also raise hands and we'll get to you as much as we can. We've got about 15 minutes for questions. Kristen, did you want to jump in and voice your question, or should I just do it?
I can voice it. Can you hear me okay?
Great. Yep.
So my question is, did you tie in suppression strategy? You had a number of fires, especially in Northern California. You talked about the red salmon, where large burnouts were part of the strategy. I'm not sure if you took that into consideration when you were talking about how you viewed them. as its size. And that's, I guess, one of the things that very fundamental is not necessarily the burning attribute. Obviously, it doesn't change emissions because that's emissions are emissions, but that strategy does, especially the length or duration of an incident and how you might have peaks throughout the length of that fire. That strategy is pretty key.
Yeah, well, thank you for the question. That is a good question. I can say that for the red salmon fire, what we were mostly doing there was just showing that we could have a late peaking fire, and that the data set that we have was able to pick up fires that had very small emissions and then could continuously pick up those emissions until they blew up later. So just showing the capability of the data set. But to answer your question, we did not include any sort of suppression strategies or like causes of ignition or anything like that in this. I think we would be totally interested in doing so if we could somehow find data sets for those that played nicely with what we have. The main goal from us was to really just try to look at as many fires we could, as many days of as many fires as we could across California, and not specifically look for certain fires. And so that sort of limited us because a lot of ignition knowledge or suppression strategies is done on like a very individual fire basis. And so it was just hard for us to get data that looked like that. So if those did exist, that'd be great for us to incorporate for future work. That's definitely something we are interested in, and know it's like a shortcoming of the data that we're using here.
Thank you. Thanks for the question. I'll just go to the next in order. A couple of questions from Brian Potter. Brian, do you want to speak up or have me? Perfect.
Sure, I'll take it. Patrick, I want to encourage you to dig into or to read the terminology used in fire science very carefully, because, I mean, this is preface to my question. Your use of severity and regime totally threw me, and I'm a meteorologist. Those are terms used in fire for ecological purposes. And hearing them throughout this, it kept throwing my brain into fire ecology territory, and I honestly got lost partway through and had to come back and really concentrate to follow. The question I first posted, though, was about the emissions algorithm. And you showed the scatter plots where there were a lot more emissions when the dryness was high, yet the wind speed didn't seem to make much difference. I would suspect very strongly that that is a consequence of the method used to calculate the emissions. Fuel consumption and emissions have totally different calculation processes than fire behavior. So if you're looking at fire behavior, emissions aren't the same. If you're looking at fire emissions, consumption is not the same. So I would strongly encourage you to go into the literature on the fire, on the emissions algorithms used for your data to make sure you understand what it's actually showing you in these figures. I like the figures, but that was the first thing that hit me as soon as I saw them, was wind didn't seem to matter and dryness was overlord.
Well, yes, thank you, Brian, for your comments. I'm definitely apologize about the severity and regime to people that are fire ecologists. This is something that I was fixing yesterday in my paper, actually, and I did not get to it in time for the talk just because I've run out of time with doing masters and this and paper all on top of each other. So sorry about that. Yes, my understanding of fire severity is that it usually relates to like the ecological consequences. So like percent of basal area burned or percent of stems burned, etc. So sorry that I overlapped some terminology there. I've switched it all over to high emissions for the future. Regarding your question about emissions, though, or your statement, my understanding of our data set is that I can try to scroll through this quickly, is that the emissions model comes from daily burned area from MODIS. So the main factor or the main constraint of the emissions is this daily burned area. And if you do have winds physically spreading the fire, you're going to have more burned area and larger emissions. That daily burned area is then, of course, aggregated and run through the emissions model. So that's the main reason that savanna fires typically have fewer emissions than forest fires. But it does come from satellite observations of the fire. So I don't know if I'm answering your question directly, but it should, I mean, should be dependent on wind speed if wind is in fact spreading the fire and causing more burned area.
It is in a sense, but obviously from your data, the dryness is overpowering any wind signal on your scale. Burned area is one piece of what goes into an emissions model. I am not an emissions expert, but I would strongly encourage you to talk to someone like Susan O'Neill in the Seattle Fire Lab who published a lot of work on the emissions, or Sean Urbanski from Missoula, Susan Pritchard. But it's one of those things that while it is somewhat tangential to the thrust of your work, one misworded statement undermines your credibility in your presentations and things. And I will also throw out that you're in Seattle, I'm in Seattle. I'd be more than happy to meet you at a socially distanced restaurant, bar, coffee shop and talk over a bunch of this stuff. I'd be more than happy to do that. Cliff knows where to find me.
Thank you.
All right. Thank you, Brian. And the next person in line, we have Helen Smith. Helen, you want to give the context, your question and the context with it?
Yeah, thanks, Chris. On one of your slides, you mentioned winter storm, and I'm wondering if you really mean a cold front, since we're talking about the fire season.
Yeah, so winter, when I do say winter storms, what I'm talking about are mid-latitude cyclones. So these events basically distort the temperature field, and these low pressures will wrap down cold air from the north and warm air from the south, which generates a cold front and a warm front. So within these cyclones, these are actually probably occluded at this point, but there is, or maybe there's a cold front coming down from the upper left. We have this clear cloud-free section and then warm air to the right. So when I say winter storms, that I guess does include the cold sector of them. So the fires here, the winds were being driven by the cold high-pressure air left over from that comma-shaped mid-latitude cyclone to the right. Does that answer your question?
Yeah, it does. I think similar to what Brian brought up, these terms are just, it's really difficult when we in the fire world are used to certain terms, and winter storm doesn't kind of compute in our brains when we're talking about the middle of the fire season. So I was just wanted to be clear.
Yeah,
Thank you.
it is the same type of event is what we're talking about. Sorry about that.
Great. Thank you, Helen. I have one more in the question in the chat box. Alina Kanzler, nice to see you in the chat box. Alina, do you want to put your question out there, or would you like me to say it?
Yeah, you can go ahead and read it.
Okay. So Alina asks, if the interactions between wind and vapor pressure deficit is important, would you consider plotting the change in frequency of them both being above the identified thresholds? And if you did show this and I missed it, I apologize.
Yes, correct. I'll go back to it. I think I'm understanding your question, and I think I did show it. So this is the total frequency of both the vapor pressure deficit threshold and the wind threshold occurring at the same time, and the change in that over time for the last 40 years, where it's pretty much getting worse everywhere. This is the change in wind for pretty much the last 40 years threshold. where it's actually improving in a lot of regions, or I guess improving is a funny word because I come from wind energy, where this would be not improving in many regions. But then in dryness, it's getting a lot worse and a lot more dry everywhere. So hopefully I answered your question, but maybe I misunderstood it. So if I did, just let me know.
Yeah, I just missed the wind on that first one.
Yes,
So if you look at that, or go back to the one where you're showing the interaction, both wind,
this one, yes.
yeah. So it's really, it's not everywhere in the whole state. There's some gaps. That's interesting. I wonder, does this change over time, and where it's spatially clustered, does it correspond with where you were seeing spatially the highest emissions?
It corresponds pretty well to where we're seeing the highest emissions, but I should mention that the emissions data set we only have for 18 years, whereas this we have for 40 years, so we can't, I guess, compare it as thoroughly, and it'd be hard to make trends with emissions for 18 years. So I don't know. I mean, there is a lot going on with fire emissions. Like I mentioned, there's ignitions, there's times of previous fire exclusion or like forest mismanagement in certain regions. So weather is just a part of it, but I think in general, a lot of the weather getting worse might correspond. Like you could probably say that it does correspond to some of the areas that we do care about, knowing where the fire emissions do tend to happen. So.
Well, it looks like we have time for maybe one more question, and Kara, the Yedinak has her hand up.
Thanks, Chris. You did well.
Thank you.
I was curious when so it sounds like the emissions data is coming from satellite
Yes.
data across 18 years. How are you picking fire and fire areas where there are no structures present? Because I'm hearing that you're assigning these emissions to different forest types or different land cover types, but the locations of the fires appear to be in places that are populated. So I'm wondering if structures could be a component to those emissions.
Yes, that is a good question. I think my understanding, like Brian mentioned, I do want to look at the emissions data set in a bit greater detail and talk with those people. My understanding is that the emissions come just from like the actual ecological land cover there and fuels. So I don't actually, like, I'm not choosing the spatial areas being burned. That's all happening before it gets to me. What I'm only seeing is these little squares of aggregate emissions for a certain region. So I don't actually know within that region what's burning, whether it's like houses or savanna or trees. I just trust that it was given to me correctly from the data set.
Okay. As far as I'm aware, there's no way to parse out emissions specific to structures versus emissions specific to wildland spaces when you're using satellite data. So I'm guessing that you're looking at a combination of both. But yeah, definitely check in with the other folks to get a better sense of that.
Yeah, I'm not too certain. That's just my understanding from the way that I read their papers from. I don't want to mispronounce the name, but I think it's like Giglio et al. Work on the GFED, so with MODIS data.
Thanks.
Well, I think that's all we have time for today. Thanks everyone for the great questions, and Patrick, great job. Appreciate your presentation today. I will share my screen now for our next upcoming, if I can do it right. Can we, does that show up right? With our next presentation will be February 10th. Alex Lookenbiel from the Missoula National, or the weather office in Missoula for he's a meteorologist for National Weather Office. This was set up by our own and most recent seminar coordinator, and Natalie has given up the spot, and I am filling in for her the best I possibly can. So thank you so much, Natalie, for all your efforts through the years. You've certainly made it easier for me to slide into the role. And that is it for now. Please be sure to let me know if you have folks that you would like to give another seminar in the future. We'll pretty well booked for the spring semester, but we will have openings